To understand planets, we first have to understand why the word itself has been so difficult to define. For most of human history, a planet was not a scientific object but a moving light in the sky. Ancient astronomers noticed that certain points of light wandered against the fixed background of stars. The Greeks called them planets, meaning wanderers. This definition had nothing to do with size, shape, composition, or origin. It was purely observational. If it moved differently than the stars, it was a planet. Under this view, the sun and the moon distance from the central star plays a decisive role in what kind of planets form. Close to the star, temperatures are high. Only metals and rocky materials can survive without vaporizing. This is why inner planets tend to be small, dense, and rocky. Farther out where temperatures drop, ices can form. These include frozen water, methane, and ammonia. Beyond a critical boundary known as the frost line, protoplanets can grow much larger because more solid material is available. In these colder regions, some protoplanets grow massive enough to attract thick envelopes of gas before the disk dissipates. These become gas giants, with deep atmospheres dominated by hydrogen and helium. If they form slightly later or in regions with less gas, they may become ice giants instead, composed largely of heavier volatile compounds with thinner atmospheres. Timing is crucial. Protoplanetary disks only last a few million years before stellar radiation blows the remaining gas away. Planet formation is not a peaceful process. Collisions can be violent and transformative. Giant impacts can strip atmospheres, alter rotation rates, and even create moons. Many scientists believe that Earth's moon formed after a Mars-sized body collided with the early Earth, ejecting debris that later coalesced. Such events are common in young planetary systems and play a major role in shaping final planetary characteristics. Migration adds another layer of complexity. Planets do not always stay where they form. Interactions with the gas disk and with other planets can cause them to move inward or outward over time. This explains why astronomers have found massive gas giants extremely close to their stars in other systems, so-called hot Jupiters. These worlds likely formed farther out and migrated inward, reshaping their systems as they move. Not all material ends up in planets. Leftover debris can form asteroid belts, comet reservoirs, or be ejected entirely from the system. Some planets may be thrown into interstellar space through gravitational encounters, becoming rogue planets that wander the galaxy without a star. What emerges from this process is not a neat arrangement, but a dynamic system shaped by physics, chance, and time. Every planet carries a record of its formation and its composition, orbit, and structure. By studying how planets form, scientists are not just explaining our own solar system, they are uncovering the rules that govern planetary systems throughout the universe. The birth of our solar system began about 4.6 billion years ago, long before any planet had a surface, an atmosphere, or even a stable orbit. At that time, a massive cloud of gas and dust drifted through a quiet region of the Milky Way. This cloud contained the basic ingredients of planetary construction: hydrogen and helium from the early universe, along with heavier elements produced by earlier generations of stars that had lived, exploded, and seeded space with enriched material. Gravity was the catalyst. As a region of the cloud grew denser than its surroundings, it began to collapse inward. Conservation of angular momentum caused the collapsing material to spin faster, flattening into a disk. At the center of this disk, pressure and temperature rose until nuclear fusion ignited. A star was born, marking the beginning of the sun's long life. Around it, the remaining material formed a rotating circumstellar disk that would eventually give rise to planets, moons, asteroids, and comets. This early solar system was anything but orderly. Temperatures varied dramatically with distance from the newborn sun. Close in, heat prevented volatile substances from condensing, leaving only refractory materials like This mass disparity has consequences. Outer planets exert strong gravitational influence, shaping the orbits of smaller bodies and acting as cosmic gatekeepers that deflect or capture comets and asteroids. Atmospheres provide another sharp contrast. Inner planets struggle to hold onto light gases due to lower gravity and intense solar radiation. Over time, many lose much of their original atmospheres to space. Outer planets, with their enormous gravity and colder environments, retain thick atmospheres rich in hydrogen and helium. These atmospheres host complex weather systems, powerful storms, and extreme pressure conditions unknown on rocky worlds. The internal heat of planets also differs between these groups. Inner planets rely largely on residual heat from formation and radioactive decay within their cores. This heat drives processes such as volcanism and tectonics, though these processes tend to diminish over time as the planets cool. Outer planets, however, often emit more energy than they receive from the sun. Gravitational compression and slow contraction generate internal heat that fuels dynamic atmospheric activity for billions of years. Rotation and magnetic fields further separate inner and outer planets. Rocky planets typically rotate more slowly and generate magnetic fields only if they have molten, conductive cores and sufficient rotation. Gas and ice giants rotate rapidly, producing enormous magnetic fields that trap radiation and create vast magnetospheres. These invisible structures can extend millions of kilometers into space and strongly affect surrounding moons. Moons themselves highlight another distinction. Inner planets have few or no moons, and those they possess tend to be small. Outer planets host extensive satellite systems, some with dozens of moons ranging from tiny fragments to large, planet-sized bodies with their own atmospheres and geological activity. These moon systems function like miniature solar systems, offering additional laboratories for studying planetary processes. Despite these contrasts, inner and outer planets are part of a continuous spectrum rather than isolated categories. Discoveries of exoplanets have revealed worlds that blur the line, such as super-Earths and mini-Neptunes that do not exist in our solar system. Still, the inner-outer division remains a powerful framework for understanding how temperature, distance, and material availability shape planetary outcomes. It reminds us that where a planet forms is often just as important as what it is made of. Planetary motion is governed by a small set of physical principles that produce an extraordinary range of behaviors. At the most basic level, planets move because gravity pulls them toward their star, while their forward motion prevents them from falling straight in. The result is an orbit, a continuous state of falling around a central body rather than into it. This balance between gravity and motion is what gives planetary systems their structure and long-term stability. Orbits are not perfect circles. They are ellipses, meaning they have a slight oval shape with the star located at one of the two focal points. This fact was first described mathematically by Johannes Kepler in the early 17th century. His laws of planetary motion revealed that planets move faster when they are closer to the star and slower when they are farther away. This variation in speed is not random. It conserves angular momentum and reflects how gravity behaves over distance. The shape of an orbit is described by its eccentricity. A perfectly circular orbit has an eccentricity of 0, while more elongated orbits have higher values. In our solar system, most planets have low eccentricities, resulting in relatively stable climates over long periods. More eccentric orbits can lead to extreme seasonal changes, as the distance between planet and star varies significantly during each revolution. Revolution refers to a planet's movement around its star, while rotation describes how the planet spins on its own axis. These two motions planet can rotate quickly but take a long time to orbit its star, or vice versa. This diversity explains why planetary days and years vary so dramatically across the solar system. Axial tilt adds another layer of complexity. A planet's axis is rarely perfectly perpendicular to its orbital plane. This tilt determines how sunlight is distributed across the planet's surface throughout its orbit. Moderate tilt can produce seasons, while extreme tilt can lead to unusual patterns of light and darkness. A planet with little or no tilt experiences minimal seasonal variation, while one with a large tilt may undergo radical shifts in climate over the course of its year. Orbital planes themselves tend to align because planets form from a rotating disk of material. As a result, most planets orbit within roughly the same plane and in the same direction. Deviations from this pattern usually indicate past gravitational disturbances, such as close encounters with other planets, or the influence of massive bodies that altered orbital paths. Gravity does not act in isolation. Planets interact with one another, subtly exchanging energy and momentum. These interactions can lead to resonances, where orbital periods lock into simple ratios. Resonances can stabilize or destabilize orbits, sculpting the architecture of planetary systems. Over long timescales, even small gravitational nudges can accumulate into significant changes. Tidal forces are another consequence of orbital motion. When a planet is close to its star or a large moon, gravity can stretch and deform it. This process dissipates energy as heat and can alter rotation rates. Over time, tides can cause planets or moons to become tidally locked, always showing the same face to the body they orbit. This has profound implications for climate, atmospheric circulation, and habitability. Planetary motion is not static. Orbits evolve slowly due to gravitational interactions, mass loss, and external influences. While these changes usually occur over millions or billions of years, they shape the long-term fate of planets and entire systems. Understanding planetary motion is therefore essential not just for predicting where a planet will be, but for understanding how planetary systems form, change, and sometimes fall apart. Mercury is the closest planet to the Sun, and in many ways the most extreme. Its proximity to the Sun exposes it to intense radiation and gravitational forces that shape nearly every aspect of its behavior. Despite being one of the smallest planets, Mercury holds outsized importance in planetary science because it reveals how worlds behave under harsh stellar conditions. Mercury is only slightly larger than Earth's moon, yet it is extraordinarily dense. A large fraction of its volume is occupied by a massive iron-rich core, far larger in proportion than that of any other planet. This suggests that Mercury either formed with an unusually high metal content or lost much of its original rocky mantle early in its history, possibly due to violent collisions or intense solar heating during the solar system's infancy. Its interior structure provides key evidence about early planetary differentiation and the chaotic environment near the young sun. The planet's surface tells a story of ancient violence. Mercury is heavily cratered, resembling the moon more than Earth. These craters formed during a period of intense bombardment early in the solar system's history, when leftover debris collided with forming planets. Unlike Earth, Mercury lacks active plate tectonics and significant erosion, so these scars remain largely unchanged for billions of years. However, the surface is not entirely static. Long, curved cliffs known as scarps crisscross the planet, formed as Mercury cooled and contracted over does not rotate once for every orbit around the Sun. Instead, it is locked in a 3-2-spin orbit resonance, meaning it rotates 3 times for every 2 trips around the Sun. This produces a strange solar day. One sunrise to the next on Mercury lasts about 176 Earth days. This slow rotation contributes to the planet's extreme temperature differences and creates regions near the poles that never receive direct sunlight. These permanently shadowed polar craters hold one of Mercury's greatest surprises, water ice. Despite the planet's proximity to the Sun, radar observations and spacecraft data have confirmed the presence of frozen water in these cold traps. The ice likely arrived via comet impacts and has remained preserved because the crater floors never warm above freezing. This discovery reshaped scientific understanding of how water can survive even in the inner solar system. Mercury also possesses a global magnetic field, a feature once thought impossible for such a small planet. Although much weaker than Earth's, this magnetic field indicates that Mercury's core is at least partially molten and capable of generating a dynamo. The field interacts directly with the solar wind, producing a dynamic magnetosphere that is constantly reshaped by the Sun's activity. Exploration of Mercury has been challenging due to the Sun's overwhelming influence. Spacecraft must carefully manage heat and energy while navigating the planet's strong gravitational environment. Missions have revealed Mercury as a world of extremes, small yet dense, ancient yet dynamic, scorched yet icy. Studying Mercury helps scientists understand not only our own solar system's inner boundary, but also the many rocky exoplanets discovered orbiting perilously close to their stars. Venus is often called Earth's twin because of its similar size, mass, and composition. Yet in reality, it is one of the most hostile worlds ever studied. If Mercury shows what happens to a small planet under intense solar influence, Venus demonstrates how a planet similar to Earth can evolve into something radically different through atmospheric processes alone. Its story is a warning written on a planetary scale. At first glance, Venus appears deceptively calm. Thick clouds permanently cover the planet, reflecting sunlight and giving it a bright, uniform appearance when seen from space. Beneath those clouds, however, lies an environment of crushing pressure and extreme heat. Surface temperatures average around 460 degrees Celsius, hotter than Mercury despite Venus being farther from the Sun. This heat is not primarily caused by proximity to the Sun, but by a runaway greenhouse effect driven by its atmosphere. Venus's atmosphere is extraordinarily dense, composed mostly of carbon dioxide with clouds of sulfuric acid. The atmospheric pressure at the surface is more than 90 times that of Earth, equivalent to being nearly a kilometer underwater on our planet. This thick blanket traps heat with devastating efficiency. Once greenhouse warming intensified, any surface water would have evaporated, adding water vapor to the atmosphere and accelerating heating even further. Over time, ultraviolet radiation from the Sun split water molecules apart, allowing hydrogen to escape into space and leaving Venus permanently dry. The surface of Venus is hidden from optical view, but radar mapping has revealed a landscape dominated by vast volcanic plains, towering shield volcanoes, and enormous lava flows. Unlike Earth, Venus shows little evidence of plate tectonics. Instead of multiple moving plates, its crust appears to act as a single rigid shell. Heat builds up beneath this shell over long periods, potentially released in catastrophic resurfacing events where massive volcanic activity renews large portions of the planet's surface at once. Venus's geology suggests it is still volcanically active, or at least was so in the recent geological past. Observations of atmospheric gas fluctuations and surface changes hint that eruptions may still occur. If confirmed, This would make Venus one of the few bodies in the solar system with ongoing large-scale volcanism. Such activity plays a key role in maintaining its thick atmosphere by continually releasing gases from the interior. One of Venus's most puzzling traits is its rotation. The planet spins extremely slowly and in the opposite direction of most planets, meaning the sun would appear to rise in the west and set in the east. A single rotation takes longer than a full orbit around the sun, so a day on Venus is longer than its year. The reasons for this backward, sluggish spin remain debated, but possible explanations include massive early impacts or long-term atmospheric tidal effects that gradually altered its rotation. Despite its harsh surface, Venus has regions in its upper atmosphere where temperatures and pressures are surprisingly Earth-like. This has led to speculation about whether microbial life could exist in the cloud layers, suspended far above the deadly surface. While no evidence of life has been confirmed, unusual chemical signatures have renewed interest in studying Venus as more than just a cautionary tale. Exploration of Venus has been difficult due to its extreme conditions. Landers survive only hours before succumbing to heat and pressure. Yet the planet remains a priority for future missions because it holds answers to fundamental questions about planetary climate, atmospheric evolution, and habitability. Venus shows that being Earth-sized and Earth-like in origin does not guarantee an Earth-like future. Its transformation into a furnace world illustrates how fragile planetary balance can be and how dramatically a planet's fate can change. Earth is the only known planet where life has emerged and persisted for billions of years, making it the benchmark against which all other worlds are measured. Its uniqueness does not come from a single feature, but from a rare combination of conditions that together create long-term stability and habitability. Understanding Earth as a planet requires stepping back and seeing it not as a home, but as a complex physical system shaped by cosmic forces. Earth formed from the same protoplanetary disk as its neighboring planets, yet its position proved decisive. Located within the sun's habitable zone, Earth receives just enough energy to allow liquid water to exist on its surface. This balance has remained stable over geological timescales, despite variations in solar output and internal activity. Water, in turn, became a powerful agent of change, sculpting the surface, regulating climate, and enabling chemistry complex enough to support life. One of Earth's defining features is its atmosphere. Composed primarily of nitrogen and oxygen, it differs dramatically from the carbon dioxide-dominated atmospheres of its neighboring planets. This composition is not accidental. It is the product of billions of years of geological activity and biological feedback. Volcanic outgassing supplied early gases, while photosynthetic life transformed the atmosphere by releasing oxygen. This oxygen not only enabled complex life, but also formed an ozone layer that shields the surface from harmful ultraviolet radiation. Earth's internal structure plays a crucial role in its behavior. A large, partially molten iron core generates a strong magnetic field that extends far into space. This magnetosphere deflects charged particles from the solar wind, protecting the atmosphere from erosion and preserving surface conditions. Without this magnetic shield, Earth might have lost much of its atmosphere long ago, as happened to some other rocky planets. The planet's surface is constantly reshaped by plate tectonics, a process unique among known worlds. Earth's crust is divided into multiple moving plates that float atop a convecting mantle. Their interactions create mountains, trigger earthquakes, recycle crustal material, and regulate atmospheric carbon dioxide through long-term chemical cycles. This geologic activity acts as a planetary thermostat, helping maintain temperatures suitable for liquid water over immense spans of time. relatively rapid rotation creates a stable day, night cycle that moderates temperature differences, while a moderate axial tilt produces seasons without extreme climatic swings. These rhythmic patterns influence weather systems, ocean circulation, and biological cycles. Oceans themselves cover more than 2/3 of the planet's surface, storing heat and redistributing it globally, further stabilizing climate. The presence of a large moon has also shaped Earth's evolution. Gravitational interactions between Earth and its moon stabilize the planet's axial tilt, reducing chaotic variations that could otherwise cause severe climate instability. Tides generated by this interaction influence ocean mixing and may have played a role in the early development of life by concentrating chemicals along ancient shorelines. From space, Earth appears as a dynamic living planet. Clouds swirl, continents drift, ice advances and retreats, and life alters the chemistry of the air and oceans. These changes are not superficial. They are interconnected processes that feed back into one another. Earth is not static, but it is resilient, capable of absorbing shocks while maintaining overall balance. Studying Earth as a planet allows scientists to understand both its fragility and its endurance. It provides a reference point for interpreting other worlds, especially those that appear similar in size or location. Earth's long-term habitability is the result of fortunate initial conditions combined with self-regulating systems that emerged over time. In the search for life elsewhere, Earth remains both a guide and a reminder that planetary success depends on harmony between geology, atmosphere, and energy. Mars has long captured human imagination as the planet most similar to Earth and the most likely candidate for past or present life beyond our world. Though smaller and colder than Earth, Mars preserves a rich geological record that reveals a dramatically different past. Today it is a dry, dusty desert world, but its surface tells a story of rivers, lakes, and environments that may once have supported life. Mars formed from the same material as Earth, but ended up with only about 1/10 of Earth's mass. This difference had profound consequences. With weaker gravity, Mars struggled to retain a thick atmosphere over long periods. Early in its history, the planet likely possessed a denser atmosphere and surface water. Geological features such as valley networks, delta formations, and sedimentary layers indicate that liquid water once flowed across its surface, shaping the landscape over millions of years. The loss of Mars's atmosphere is central to its transformation. Unlike Earth, Mars lacks a strong global magnetic field. Without this protective shield, the solar wind gradually stripped away atmospheric gases. As pressure dropped, surface water became unstable, freezing or evaporating into space. Over time, Mars transitioned from a potentially habitable world to the cold, arid planet observed today. Traces of water remain locked in polar ice caps and buried beneath the surface. Mars's surface geology is among the most diverse in the solar system. It hosts the largest volcano known, Olympus Mons, a shield volcano so massive that it would dwarf any mountain on Earth. Its immense size was made possible by the absence of plate tectonics. The planet's crust does not move, allowing magma to erupt repeatedly at the same location. Mars also features vast canyon systems, including Valles Marineris, which stretches thousands of kilometers and reaches depth far exceeding Earth's Grand Canyon. The planet's reddish color comes from iron oxide, rust coating its surface. This oxidation process reflects the interaction between iron-rich rocks and oxygen, likely derived from ancient water and atmospheric processes. Dust storms are common on Mars, ranging from small local events to planet-wide storms that can obscure the entire surface for weeks. These storms play a major role in shaping the planet's climate and surface features. Mars's average surface temperatures are well below freezing, and atmospheric pressure is less than 1% of Earth's. Despite this, seasonal changes occur as carbon dioxide freezes and sublimates at the poles, causing the atmosphere itself to expand and contract annually. These cycles drive winds and influence dust activity across the planet. One of the most compelling aspects of Mars is its potential for life. While surface conditions today are harsh, subsurface environments may still harbor liquid water, protected from radiation and extreme temperatures. Organic molecules have been detected in Martian rocks, and seasonal methane fluctuations suggest active chemical processes. Whether these signals arise from geological or biological sources remains an open question. Mars has been explored more extensively than any other planet besides Earth. Orbiters map its surface in exquisite detail, while rovers analyze rocks, soil, and atmospheric chemistry. Each mission adds to a growing picture of a planet that once may have resembled early Earth in key ways. Understanding why Mars lost its habitability, while Earth retained it, offers crucial insight into planetary evolution. As humanity looks toward future exploration, Mars stands as both a destination and a lesson. It shows how small differences in mass, magnetic protection, and atmospheric retention can determine a planet's fate. Mars is not a failed Earth, but a world that followed a different path, one that helps illuminate the delicate balance required for long-term habitability. Beyond the major planets lies a population of smaller bodies that play an outsized role in shaping planetary systems. Asteroids, meteoroids, and related objects are remnants of the formation process, material that never became part of a planet or that was broken apart through collisions. Though often treated as background debris, these bodies are essential for understanding how planets evolve, interact, and sometimes face catastrophic change. Asteroids are primarily rocky or metallic objects that orbit the Sun. Most are found in a broad region between Mars and Jupiter, known as the asteroid belt. This region is not densely packed, but it contains millions of objects ranging from dust-sized grains to bodies hundreds of kilometers across. Many of these objects are leftovers from the early solar system, preserved in a relatively stable gravitational environment. Their compositions vary widely, reflecting the temperature gradients and chemical diversity present during planetary formation. The asteroid belt exists largely because of Jupiter's influence. The immense gravity of the gas giant prevented material in that region from coalescing into a planet. Instead, gravitational perturbations kept objects fragmented and dynamically excited. Over time, collisions ground many asteroids down into smaller pieces, creating a population shaped by both accretion and destruction. Studying these objects provides direct insight into the building blocks of planets. Meteoroids are smaller fragments derived from asteroids or comets. When they enter a planet's atmosphere and burn up, they produce meteors, commonly known as shooting stars. If a fragment survives passage through the atmosphere and reaches the surface, it becomes a meteorite. These meteorites are scientifically invaluable. Some are among the oldest solid materials known, formed before any planet fully assembled. By analyzing them, scientists can measure isotopic compositions that reveal the age, chemistry, and thermal history of the early solar system. Asteroids are not static hazards drifting aimlessly through space. Their orbits evolve due to gravitational interactions with planets and subtle forces such as sunlight-driven heating. Over long periods, these effects can nudge asteroids out of stable regions and send them toward the inner solar system. This is why near-Earth asteroids exist and why impact risk, while low at any given time, is never zero. Impacts have played a defining role in planetary history. Early in the solar system's life, planets endured heavy bombardment that reshaped their surfaces and interiors. Large impacts can melt crusts, strip atmospheres, and alter rotation rates. On Earth, impacts may have influenced the conditions under which life emerged, delivering water and organic molecules while also causing mass extinctions. The most famous example is the impact linked to the extinction of the dinosaurs, demonstrating how small bodies can radically alter biological history. Asteroids also act as delivery systems. Carbon-rich asteroids contain complex organic compounds and water-bearing minerals. When such objects collide with young planets, they may contribute essential ingredients for habitability. This idea has led scientists to view asteroids not only as threats, but also as potential sources of life-enabling materials. In addition to the main asteroid belt, populations of small bodies exist throughout the solar system. Trojan asteroids share orbits with planets, clustering around stable gravitational points. Others are scattered into distant reservoirs or ejected entirely into interstellar space. Each population reflects a different chapter of dynamical evolution and gravitational interaction. Understanding asteroids and meteoroids is also crucial for planetary defense and future exploration. Tracking near-Earth objects allows scientists to assess potential impact risks and develop mitigation strategies. At the same time, asteroids are seen as potential resources, containing metals and volatiles that could support future space activity. These small bodies may lack the grandeur of planets, but they are fundamental to planetary science. They preserve ancient material, influence planetary environments, and remind us that planetary systems remain dynamic long after their formation. In many ways, asteroids and meteoroids are the connective tissue of the solar system, linking its violent past to its evolving present. Jupiter dominates the solar system in both size and influence. With a mass more than twice that of all other planets combined, Jupiter is less a planet in the ordinary sense and more a miniature planetary system of its own. Its immense gravity has shaped the architecture of the solar system from its earliest moments, influencing the formation, movement, and survival of countless other bodies. Jupiter is a gas giant, composed primarily of hydrogen and helium, the same elements that make up the Sun. Unlike rocky planets, it has no solid surface in the traditional sense. Instead, its atmosphere gradually transitions into deeper layers of compressed gas and liquid as pressure increases with depth. Far below the visible cloud tops, hydrogen is thought to enter exotic states, eventually becoming metallic hydrogen capable of conducting electricity. This unusual interior is key to many of Jupiter's defining characteristics. One of the most striking features of Jupiter is its atmosphere. Thick bands of clouds encircle the planet, driven by powerful jet streams that can reach hundreds of kilometers per hour. These bands are the result of complex atmospheric circulation patterns caused by rapid rotation and internal heat. Jupiter completes a full rotation in just under 10 hours, making it the fastest spinning planet in the solar system. This rapid spin flattens the planet slightly at the poles and intensifies atmospheric dynamics. Embedded within Jupiter's cloud layers are massive storms, the most famous of which is the Great Red Spot. This enormous vortex has been observed continuously for more than 3 centuries. It is large enough to engulf Earth and persists, because Jupiter lacks a solid surface to disrupt it. Although the storm has been slowly shrinking in recent decades, it remains a powerful symbol of the planet's turbulent nature and a natural laboratory for studying atmospheric physics on a colossal scale. Jupiter emits more energy than it receives from the Sun. This excess heat comes from slow gravitational contraction and residual heat left over from its formation. As the planet gradually compresses under its own gravity, it releases energy that drives convection deep within its atmosphere. This internal heat source is why Jupiter's weather systems are so active and long-lived compared to those of terrestrial planets. The planet's magnetic field is the strongest of any planet in the solar system. Generated by the motion of metallic hydrogen in its interior, Jupiter's magnetosphere is immense, extending millions of kilometers into space. It traps high-energy particles and creates intense radiation belts that pose serious challenges for spacecraft. This magnetic environment also interacts with Jupiter's moons, producing electrical currents and auroras far more powerful than those seen on Earth. Jupiter's role as a gravitational guardian is complex. Its massive pull can deflect comets and asteroids away from the inner solar system, potentially reducing impact risks for smaller planets. At the same time, its gravity can also redirect objects inward, sending them toward the inner planets. Whether Jupiter is more protector or threat remains debated, but there is no doubt that it strongly influences the flow of small bodies throughout the solar system. The planet's extensive system of moons further emphasizes its importance. Dozens of natural satellites orbit Jupiter, ranging from small, irregular fragments to large, planet-like worlds. These moons are shaped by Jupiter's gravity and radiation, creating environments of intense geological activity, subsurface oceans, and complex interactions. Together, Jupiter and its moons form a miniature model of a planetary system, offering insights into processes that operate on much larger scales around stars. Studying Jupiter is essential for understanding not only gas giants, but planetary systems as a whole. Similar planets have been found orbiting other stars in vast numbers, often playing the same dominant role Jupiter does in our own system. By examining Jupiter's structure, atmosphere, and influence, scientists gain a deeper understanding of how giant planets form, how they shape their surroundings, and how they affect the potential for life elsewhere in the universe. A planetary atmosphere is far more than a layer of gas surrounding a world. It is an active system shaped by gravity, chemistry, radiation, and time, capable of transforming a planet's surface and determining whether it can support liquid water or life. Atmospheres regulate temperature, drive weather, protect surfaces from radiation, and record the history of planetary evolution. Their presence, or absence, often marks the difference between a barren world and a dynamic one. Atmospheres form through several pathways. During a planet's early history, gases can be captured directly from the protoplanetary disk, especially if the planet is massive enough to hold onto light elements like hydrogen and helium. This process dominates for giant planets. Smaller, rocky planets typically build secondary atmospheres through volcanic outgassing, releasing gases trapped within their interiors. Additional contributions come from comet and asteroid impacts, which can deliver water vapor, carbon dioxide, and other volatiles. Once formed, an atmosphere is constantly modified by internal and external forces. Gravity determines how well a planet can retain gases. Small planets with weak gravity struggle to hold onto light molecules, which can escape into space over time. Temperature also matters. Higher thermal energy allows gas particles to reach escape velocity more easily. This is why planets closer to their star, or with low mass, tend to lose atmospheres more rapidly. Stellar radiation plays a decisive role in atmospheric evolution. Ultraviolet light can break molecules apart in a process known as photodissociation. Lighter components, such as hydrogen, are especially vulnerable to escape once freed. Over billions of years, this can dramatically alter atmospheric composition. The difference between the thick, crushing atmosphere of Venus and the thin, fragile atmosphere of Mars is largely a story of atmospheric loss driven by solar radiation and magnetic protection. protection. Magnetic fields can slow atmospheric erosion by deflecting charged particles from the solar wind. Planets with strong magnetospheres are better shielded from direct interaction with stellar plasma. This protection helps preserve atmospheres over long timescales. Without it, a planet's atmosphere is exposed to stripping processes that gradually thin and weaken it, even if the planet once had abundant gases. Atmospheric composition determines surface conditions through the greenhouse effect. Certain gases, such as carbon dioxide, methane, and water vapor, trap heat by absorbing infrared radiation. A moderate greenhouse effect can stabilize climate and allow liquid water to exist. An extreme greenhouse effect, however, can lead to runaway heating. Venus exemplifies this outcome, where heat trapping became self-reinforcing and irreversible. By contrast, insufficient greenhouse warming can leave a planet frozen, even if it lies within a habitable orbital range. Weather and climate emerge from the interaction between atmospheric composition, rotation, and energy input. Rapidly rotating planets tend to develop strong jet streams and banded cloud patterns. Slow rotation can lead to extreme temperature differences between day and night. Atmospheric circulation redistributes heat, shapes cloud systems, and influences long-term climate stability. On planets with thick atmospheres, storms can persist for centuries, driven by internal heat rather than sunlight. Atmospheres also interact continuously with planetary surfaces. Wind erodes terrain, clouds precipitate material back to the ground, and chemical reactions alter surface minerals. Over geological timescales, these interactions can reshape entire landscapes. On some planets, surface and atmosphere evolve together through feedback loops, where changes in one drive changes in the other. One of the most remarkable atmospheric transformations occurred on Earth. Early Earth's atmosphere was radically different from today's, lacking free oxygen. Through biological processes, life altered atmospheric chemistry, introducing oxygen and enabling new forms of metabolism. This demonstrates that atmospheres are not only products of physics and chemistry, but can also be reshaped by living systems. Studying planetary atmospheres allows scientists to reconstruct a planet's past and assess its future. Atmospheric thickness, composition, and structure reveal clues about formation, internal activity, and exposure to stellar forces. As astronomers study distant exoplanets, atmospheric analysis has become one of the most powerful tools for identifying potentially habitable worlds. In many cases, the atmosphere is the planet, an evolving boundary where space, surface, and time converge. Planetary surfaces are the most direct and readable records of a planet's internal life and external history. Every crater, mountain, lava plain, fault line, or fractured ice sheet is evidence of forces that have acted over millions or even billions of years. Unlike atmospheres, which can change rapidly, surfaces preserve memory. They reveal how a planet formed, how long it stayed active, how violently it was bombarded, and how quickly it cooled. In this sense, planetary geology functions as a historical archive written in rock, ice, and dust. Across the solar system, four fundamental processes dominate surface evolution: impact cratering, volcanism, tectonic deformation, and erosion. The balance between these processes depends largely on planetary size, internal heat, gravity, and the presence or absence of an atmosphere. No two planets express these forces in the same way. Impact cratering is the most universal geological process. experiences chemical weathering under extreme heat and pressure, where surface minerals react directly with the dense atmosphere. Icy worlds introduce entirely different geological behaviors. On moons such as Europa or Enceladus, solid ice behaves like rock, while subsurface oceans act like magma. Cryovolcanism, eruptions of water, ammonia, or methane, creates fractures, ridges, and smooth plains. These processes demonstrate that geological activity does not require molten rock. It only requires energy and mobility within a material. Planetary size is critical to geological longevity. Larger bodies retain internal heat longer, sustaining volcanism and tectonics for billions of years. Smaller bodies cool quickly, becoming geologically inactive early in their history. Gravity also shapes surface features. Lower gravity allows taller mountains and broader volcanoes, while higher gravity causes terrain to relax and flatten over time. Surface composition reflects both formation conditions and evolutionary history. Rocky planets are dominated by silicate minerals and metallic cores, while icy bodies contain frozen water, organics, and volatile compounds. Color variations, such as the iron oxide red of Mars, are surface expressions of chemical processes tied directly to geology and environment. Ultimately, planetary surfaces reveal why worlds diverge so dramatically. They show how some planets remained active and dynamic, while others became frozen in time. By comparing these surfaces, scientists learn not only how planets change, but why Earth became uniquely suitable for life. Planetary geology turns distant worlds into readable histories, allowing humanity to understand its place within a much larger story written across the solar system. Moons are not merely companions to planets. They are integral components of planetary systems, shaping dynamics, geology, and long-term evolution. From tiny captured rocks to worlds larger than planets themselves, moons reveal how gravity organizes matter and how complex systems emerge around massive bodies. Studying moons expands planetary science beyond single objects and into interconnected systems governed by motion, resonance, and energy exchange. The presence of moons is closely tied to planetary mass and formation history. Large planets possess stronger gravity, allowing them to capture or retain orbiting material. The giant planets host extensive moon systems that resemble miniature solar systems, complete with inner rocky bodies, outer icy satellites, and complex orbital relationships. Smaller terrestrial planets tend to have fewer moons, often formed by rare or catastrophic events. There are several primary pathways by which moons form. Some coalesce from the same circumplanetary disk that formed their parent planet, much like planets forming around a star. This process explains the orderly, circular orbits of many large moons around gas giants. Others are captured objects, asteroids, or Kuiper belt bodies pulled into orbit by gravitational interactions. Captured moons often have irregular shapes, tilted or backward orbits, and highly eccentric paths. A third mechanism involves giant impacts. Earth's moon is believed to have formed when a Mars-sized body collided with the early Earth, ejecting material that later coalesced into a single large satellite. This event profoundly affected Earth's evolution, influencing axial stability, ocean tides, and long-term climate behavior. Without this moon, Earth's rotational axis might vary chaotically, making stable seasons unlikely. Moon systems vary dramatically across the solar system. Jupiter hosts dozens of moons, including several large ones that rival planets in size. These moons occupy resonant introducing stark hemispheric differences. Some moons are geologically active despite their small size. Io is the most volcanically active body moon, its interior heated by intense tidal forces rather than radioactive decay. Other moons, such as Europa, exhibit fractured ice surfaces and evidence of global subsurface motion, making them prime targets in the search for extraterrestrial life. Ring systems blur the boundary between moons and debris. Rings may represent failed moons that never coalesced or remnants of moons torn apart by tidal forces. Over time, ring material can clump together, forming new moons, while existing moons can shepherd rings into narrow bands through gravitational influence. Planetary systems are therefore dynamic, with matter constantly shifting between rings and satellites. Moons also influence planetary rotation and stability. Tidal interactions gradually transfer angular momentum, slowing planetary rotation and altering orbital distances. Earth's moon is slowly drifting away, while Earth's rotation is gradually slowing. Over geological timescales, these interactions reshape both bodies, demonstrating that moons and planets evolve together rather than independently. Beyond rings also interact with planetary magnetic fields and radiation environments. Charged particles within rings can be influenced by electromagnetic forces, creating complex behaviors beyond simple gravity-driven motion. These interactions provide insight into plasma physics and the coupling between solid matter and magnetic environments. Over time, rings slowly evolve. Particles may spiral inward and fall into the planet, be ejected outward, or clump together to form new moons. In this sense, rings are transitional structures, snapshots of matter in motion rather than stable end states. They represent an intermediate phase between debris and fully formed satellites. Beyond their intrinsic beauty, rings serve as natural laboratories. The same physical principles governing rings apply to protoplanetary disks around young stars and to disk galaxies on vastly larger scales. By studying rings close to home, scientists gain insight into how structure emerges in rotating systems throughout the universe. Planetary rings remind us that planets are not isolated spheres, but centers of evolving systems. They demonstrate how gravity can organize chaos into patterns of extraordinary precision, and how even fragile structures can persist when forces are balanced just right. Magnetic fields are invisible, yet they play a decisive role in shaping planetary environments. Generated deep within planets, magnetic fields extend far into space, forming magnetospheres that interact continuously with the solar wind. These fields influence radiation, atmospheric stability, surface conditions, and even the long-term potential for life. Understanding planetary magnetism reveals how internal dynamics connect directly to conditions far beyond a planet's surface. Planetary magnetic fields are produced by a process known as the dynamo mechanism. This requires three key ingredients: an electrically conductive fluid, sufficient internal heat to drive motion, and planetary rotation. In most cases, the conductive fluid is molten metal, such as liquid iron, circulating within a planet's core. As this fluid moves and twists under rotation, it generates electric currents, which in turn create a magnetic field. If any of these conditions weaken or disappear, the magnetic field fades. The strength and structure of magnetic fields vary widely across the solar system. Earth possesses a strong, global magnetic field generated by its liquid outer core. This field deflects most charged particles from the sun, forming a protective magnetosphere that shields the atmosphere from erosion. Without it, Earth's oceans and atmosphere might have been stripped away over geological time, as appears to have happened on Mars. Mars offers a stark contrast. Mars once had a global magnetic field early in its history, but as its interior cooled and core motion slowed, the dynamo shut down. Today, Mars retains only localized magnetic remnants frozen into its crust. Lacking a strong magnetosphere, the planet became vulnerable to solar wind stripping, contributing to the loss of much of its atmosphere and surface water. Among the giant planets, magnetic fields can be extraordinarily powerful. Jupiter has the strongest magnetic field of any planet in the solar system. Its magnetosphere is so vast that it would appear larger than the Sun if visible from Earth. Jupiter's rapid rotation and deep layers of metallic hydrogen generate immense electric currents, producing intense radiation belts that pose serious hazards to spacecraft and would be lethal to unprotected humans. Radiation belts form when charged particles become trapped by magnetic field lines, spiraling back and forth between a planet's magnetic poles. These particles originate from the solar wind, cosmic rays, or volcanic material ejected from moons. Jupiter's moon Io, for example, supplies large amounts of ionized material that become incorporated into Jupiter's radiation environment, demonstrating how moons can directly influence planetary magnetospheres. differences in magnetic field geometry and atmospheric composition. Not all planets possess magnetic fields. Venus lacks a significant intrinsic magnetic field, despite being similar in size to Earth. Its slow rotation likely prevents a sustained dynamo. Instead, Venus has an induced magnetosphere, formed by interactions between the solar wind and its dense atmosphere. While this provides limited shielding, it is far less effective than a true planetary magnetic field. Magnetospheres act as both shields and traps. They protect atmospheres from direct erosion, but they also confine radiation that can damage spacecraft electronics and affect surface conditions. For planets and moons, the balance between protection and exposure shapes habitability. A strong magnetic field may be a critical factor in allowing life to persist on a planet's surface over billions of years. Over time, magnetic fields evolve. As planets cool, their internal heat diminishes, weakening core convection and eventually shutting down dynamos. This transition marks a profound shift in planetary history, often coinciding with atmospheric loss and surface transformation. Magnetic fields therefore serve as indicators of a planet's internal vitality as well as its external resilience. In planetary science, magnetism connects the deep interior to the space environment. It reveals how unseen motions in a planet's core influence radiation, atmosphere, and long-term stability. Though invisible, magnetic fields quietly shape the fate of worlds, determining whether they remain protected havens or exposed relics of their former selves. Temperature is one of the most fundamental properties shaping planetary environments. It governs atmospheric chemistry, surface stability, geological activity, and the potential for life. Across the solar system, temperatures vary more extremely than anywhere on Earth, ranging from furnace-like heat to near absolute zero. These extremes are not random. They arise from predictable physical factors such as distance from the sun, atmospheric composition, rotation rate, and internal heat. Solar distance is the most obvious influence on planetary temperature, but it is far from the only one. Planets closer to the sun receive more solar energy, yet surface temperature depends on how that energy is absorbed, reflected, and retained. Albedo, the fraction of sunlight reflected back into space, plays a crucial role. A bright, reflective surface can remain cooler than a darker one at the same distance, while atmospheric behavior can overwhelm distance entirely. The hottest planetary surface in the solar system belongs not to the closest planet to the sun, but to Venus. Venus's surface temperatures exceed 460 degrees Celsius, hot enough to melt lead. This extreme heat results from a runaway greenhouse effect. Its dense atmosphere, composed mostly of carbon dioxide, traps infrared radiation with extraordinary efficiency. Once heated, Venus cannot release that energy back into space, creating a stable but hostile thermal state that has likely persisted for hundreds of millions of years. In contrast, Mercury experiences the most dramatic temperature swings. Lacking a substantial atmosphere and rotating slowly, Mercury's surface heats intensely during long days and cools rapidly during equally long nights. Daytime temperatures can soar above 430 degrees Celsius, while nighttime temperatures plunge below 170 degrees Celsius. These extremes exist only a few hundred kilometers apart, highlighting the stabilizing role an atmosphere can play. At the cold end of the spectrum lies Neptune, where average atmospheric temperatures drop below 200 degrees Celsius. At such distances from the sun, solar heating is minimal. Yet Neptune radiates more energy than it receives, indicating significant internal heat. This internal energy drives violent storms and supersonic winds, demonstrating that low temperatures do not imply inactivity. Some of the coldest known environments are not planets at all, but shadowy traps, preserving ancient material. Atmosphere's moderate temperature by redistributing heat. On Earth, winds and ocean currents transport warmth from the equator toward the poles, preventing extreme contrasts. Earth benefits from a balanced greenhouse effect that maintains liquid water while avoiding runaway heating. By contrast, Mars has a thin atmosphere that provides little insulation. As a result, surface temperatures fluctuate widely, and most heat gained during the day is lost at night. Axial tilt and rotation rate further influence temperature patterns. Planets with extreme tilts experience dramatic seasonal variation. Uranus rotates on its side, causing each pole to experience decades of continuous sunlight followed by decades of darkness. This produces unusual seasonal heating cycles unlike anything seen on Earth, though Uranus remains extremely cold overall. Internal heat can also shape temperature extremes. Tidal heating, radioactive decay, and residual heat from formation contribute energy independent of sunlight. This is especially important for moons, but planets with large interiors can also retain heat long after formation, influencing atmospheric and geological behavior, even at great distances from the sun. Temperature extremes define the boundaries of planetary behavior. They determine whether rock melts, ice flows, gases escape, or chemistry proceeds. By studying these extremes, scientists learn how planets balance energy and why similar-sized worlds can evolve into radically different environments. Temperature is not merely a measurement. It is a driving force that shapes planetary identity, stability, and destiny across cosmic time. Gravity is the force that gives planets their shape, holds their atmospheres in place, and governs how matter behaves on and around them. Though invisible, gravity determines nearly every physical condition a planet experiences, from surface pressure to geological structure and the long-term stability of oceans and air. Differences in gravity across planets produce environments that would feel profoundly unfamiliar to human bodies, machines, and even basic physical processes. At its core, planetary gravity depends on two factors, mass and radius. A planet with greater mass exerts a stronger gravitational pull, but how concentrated that mass is also matters. A compact, dense planet can have higher surface gravity than a much larger but less dense world. Gravity is therefore not simply a matter of size, but of internal composition and structure. On Earth, surface gravity provides a reference point for comparison. It shapes human physiology, atmospheric pressure, and geological balance. Earth's gravity is strong enough to retain a thick atmosphere and liquid oceans, yet weak enough to allow plate tectonics, erosion, and active surface recycling. This balance plays a critical role in Earth's long-term habitability. Lower gravity worlds behave very differently. Mars has only about 38% of Earth's surface gravity. This reduced pull makes it difficult for Mars to retain a dense atmosphere, allowing gases to escape more easily into space. Lower gravity also permits taller geological features. Volcanoes can grow much larger because their own weight does not cause them to collapse as readily. At the same time, erosion proceeds more slowly, preserving ancient landforms for billions of years. Extremely low gravity is found on small bodies such as asteroids and some moons, where surface gravity is so weak that a human could jump into space. On such worlds, loose material behaves more like a collection of floating particles than solid ground. Impacts eject debris easily, reshaping the surface with minimal energy. These environments challenge conventional notions of geology, as gravity-driven processes like landslides or sediment layering operate very differently. High-gravity planets impose opposite constraints. Jupiter, the most massive planet in the solar system, has a surface gravity more than twice that of Earth at the level of its cloud tops. This intense gravity compresses its atmosphere to enormous pressures, creating extreme conditions deep below the visible clouds. Any solid surface, if it existed, would experience crushing forces far beyond human tolerance. High gravity also causes atmospheric gases to settle into dense layers, influencing weather patterns and storm dynamics. Gravity directly affects atmospheric retention. A planet's escape velocity, the speed required for particles to leave its gravitational pull, determines whether light gases like hydrogen and helium can be held over long periods. Small planets lose these gases quickly, while massive planets retain them, explaining why gas giants are dominated by light elements while terrestrial planets are not. This distinction shapes planetary identity from the earliest stages of formation. Surface gravity also influences biological and mechanical possibilities. On low-gravity worlds, organisms, if they existed, could grow larger structures with less structural support. On high-gravity planets, compact, robust forms would be favored. For human exploration, gravity affects muscle strength, bone density, circulation, and long-term health. Prolonged exposure to reduced gravity causes significant physiological changes, demonstrating how deeply gravity shapes life, adapted to a specific world. Internally, gravity governs planetary layering. Heavier elements sink toward the center, forming dense cores, while lighter materials rise. This differentiation creates metallic cores, rocky mantles, and crusts, enabling processes such as magnetic field generation and volcanism. Without sufficient gravity, this internal separation may be incomplete, limiting geological and magnetic activity. Gravity also controls orbital relationships within planetary systems. It determines how moons form, how rings behave, and how tides operate. Tidal forces arise from gravity gradients, stretching bodies and generating heat through friction. This mechanism powers geological activity on moons and influences planetary rotation rates, demonstrating gravity's reach beyond static attraction. Ultimately, gravity defines what a planet can become. It dictates whether an atmosphere endures, whether oceans persist, whether geology remains active, and whether life has a stable platform on which to evolve. By comparing gravity across planets, scientists gain insight into why worlds diverge so dramatically despite forming from the same cosmic materials. Gravity is the quiet architect of planetary diversity, shaping worlds not through forceful motion, but through constant, inescapable pull. Planetary exploration missions are humanity's primary means of transforming distant points of light into real, measurable worlds. Through robotic probes, orbiters, landers, and rovers, scientists have been able to study planetary surfaces, atmospheres, magnetic fields, and internal structures without setting foot beyond Earth. Each mission represents years or decades of planning and carries instruments designed to answer specific questions about how planets form, evolve, and sometimes become habitable. The earliest planetary missions focused on simple flybys. These brief encounters provided the first close-up images of other worlds, revealing unexpected complexity. Early spacecraft showed that planets were not smooth or uniform, but scarred, layered, and active. Flybys also allowed scientists to measure gravity, magnetic fields, and atmospheric composition, laying the groundwork for more ambitious exploration. Orbiters marked a major leap forward. By circling a planet for months or years, orbiters can map entire surfaces at high resolution and observe changes over time. Long-term observation reveals weather patterns, seasonal variation, surface chemistry, and geological processes in action. Orbiters around Mars, for example, have tracked dust storms engulfing the planet, discovered buried ice deposits, and identified minerals that form only in the presence of water. Landers and rovers bring exploration testing soil chemistry and searching for signs of past habitability. Each rover mission builds upon previous discoveries, refining questions rather than simply repeating measurements. Exploration of the inner planets revealed stark contrasts. Venus missions encountered crushing pressures and extreme heat, forcing landers to operate for only short periods. Despite this, they returned invaluable data about atmospheric composition and surface conditions, confirming the severity of the runaway greenhouse effect. Mercury missions mapped a world dominated by craters, extreme temperature variation, and a surprisingly large metallic core. The outer planets posed different challenges: immense distances, long travel times, and intense radiation. Missions to Jupiter and Saturn revealed complex systems of rings, moons, and magnetospheres. These missions demonstrated that moons could be as scientifically important as planets themselves, uncovering active volcanism, subsurface oceans, and organic chemistry far from the sun. Some missions are designed to study multiple targets in sequence, using gravity assists to conserve fuel. By carefully passing near planets, spacecraft can gain speed and alter trajectory, turning planetary gravity into a navigational tool. This technique has enabled exploration of the outer solar system with limited propulsion, extending mission lifetimes and scientific return. Planetary missions rely on a wide array of instruments. Cameras capture visible and infrared light. Spectrometers identify chemical composition. Radar penetrates clouds or subsurface layers, and magnetometers measure invisible magnetic fields. Together, these instruments allow scientists to build integrated models of planetary behavior, linking surface observations to atmospheric dynamics and internal structure. Exploration is not limited to planets alone. Missions have targeted asteroids, comets, and moons to understand the building blocks of planetary systems. Sample return missions represent a major milestone, allowing material formed billions of years ago to be studied directly in Earth-based laboratories, with precision impossible for remote instruments. These samples provide chemical and isotopic records of early solar system conditions. Every mission carries inherent risk. Spacecraft operate far beyond the possibility of repair, often enduring extreme temperatures, radiation, and mechanical stress. Failures are inevitable, yet even unsuccessful missions contribute knowledge by refining engineering techniques and improving future designs. Planetary exploration advances through iteration as much as through triumph. Ultimately, planetary missions redefine humanity's relationship with the solar system. They turn speculation into evidence and imagination into measurement. Each successful exploration expands not only scientific understanding, but also perspective, reminding humanity that its home planet is part of a vast and varied family of worlds shaped by the same physical laws. Through these missions, planets cease to be distant abstractions and become tangible places with histories, environments, and futures of their own. Detecting planets beyond the solar system is one of the most challenging achievements in modern astronomy. These worlds are unimaginably distant, faint, and overwhelmed by the light of their parent stars. Yet through careful observation and indirect measurement, scientists have developed methods capable of revealing planets that cannot be seen directly. Each detection technique relies on subtle physical effects, turning tiny signals into profound discoveries about planetary systems across the galaxy. The most productive method for finding exoplanets is the transit technique. When a planet passes directly between its star and an observer, it blocks a small fraction of the star's light, causing a brief, periodic dip in brightness. By measuring these dips with extreme precision, astronomers can determine a planet's size, orbital period, and distance from its star. Repeated transits confirm that the signal is planetary rather than random stellar variability. This method has revealed thousands of planets, especially those orbiting close to their stars. Transit observations also allow limited study of planetary atmospheres. As starlight passes through a planet's atmospheric edge during transit, certain wavelengths are absorbed by gases such as hydrogen, sodium, water vapor, or carbon dioxide. This creates a spectral fingerprint that reveals atmospheric composition. Though challenging, this technique has transformed exoplanets from mere detections into physical worlds with measurable properties. Another foundational method is radial velocity detection. As a planet orbits a star, its gravity causes the star to wobble slightly around a common center of mass. This motion shifts the star's spectral lines through the Doppler effect, alternately compressing and stretching the observed wavelengths. By measuring these shifts, astronomers can determine a planet's minimum mass and orbital characteristics. Radial velocity measurements were responsible for many of the first exoplanet discoveries and remain essential for confirming transit detections. Direct imaging represents a more intuitive but technically demanding approach. Instead of inferring a planet's presence indirectly, astronomers attempt to block the star's light and capture photons emitted or reflected by the planet itself. This requires advanced optics, coronagraphs, and extreme contrast sensitivity. Direct imaging is most successful for large, young planets orbiting far from their stars, where heat from formation makes them glow in infrared light. Gravitational microlensing offers a different perspective. When a star passes in front of a more distant background star, its gravity acts as a lens, briefly magnifying the background light. If the foreground star hosts a planet, the planet produces a short, distinctive distortion in the lensing signal. Microlensing can detect planets at great distances from Earth, including low-mass planets and those far from their stars, but the events are one-time occurrences that cannot be repeated. Timing-based methods exploit extreme regularity in astrophysical systems. Pulsar timing, for example, detects planets by measuring tiny variations in the precise pulses emitted by rotating neutron stars. While rare and unlikely to host life, these systems demonstrate the sensitivity of detection techniques and prove that planets can form in unexpected environments. Each detection method has biases. Transit and radial velocity techniques favor large planets close to their stars, leading to early discoveries dominated by hot Jupiters. As instruments improve, detection sensitivity has expanded to smaller, Earth-sized planets and longer orbital periods. Combining multiple methods allows scientists to break degeneracies, measuring both mass and radius, and inferring density and composition. Exoplanet detection relies heavily on space-based observatories designed for long, uninterrupted monitoring of stars. By observing thousands or millions of stars simultaneously, these missions identify rare planetary signals that would be impossible to detect from the ground alone. Ground-based telescopes complement this work by providing follow-up measurements and independent confirmation. Detecting exoplanets is not simply a technical achievement. It reshapes understanding of planetary formation. The diversity of discovered systems, planets orbiting multiple stars, worlds with extreme densities, and systems unlike anything in the solar system, reveals that planetary architectures are far more varied than once imagined. Through these detection methods, planets have shifted from theoretical possibilities to a vast population of known worlds. Each new technique refines the picture, bringing humanity closer to identifying planets that resemble Earth and understanding how common or rare such worlds may truly be. The discovery of exoplanets has revealed a universe far stranger and more diverse than astronomers once imagined. Early theories of planet formation formation were based almost entirely on the solar system, leading to expectations of orderly, circular orbits and familiar planetary types. Exoplanet discoveries shattered those assumptions. Instead of distant echoes of known worlds, astronomers found planets with extreme temperatures, bizarre compositions, and orbital behaviors that defy earlier models. One of the first surprises was the existence of hot Jupiters. These are gas giants comparable in mass to Jupiter, yet they orbit extremely close to their stars, often completing a full orbit in just a few days. Under classical formation models, gas giants should form far from their stars, where icy materials are abundant. The presence of hot Jupiters implies large-scale planetary migration, where massive planets move inward after formation, reshaping entire planetary systems in the process. Even more extreme are ultra-hot Jupiters, whose dayside temperatures exceed those of some stars. On these planets, metals such as iron and titanium may vaporize into the atmosphere, condense on the cooler night side, and fall as metallic rain. Atmospheric winds reach thousands of kilometers per hour, redistributing heat across hemispheres locked in permanent day and night. These worlds challenge understanding of atmospheric physics under conditions impossible to reproduce on Earth. Another unexpected category is the super-Earth. These planets are larger than Earth but smaller than Neptune, a class absent from the solar system. Super-Earths may be rocky, ocean-covered, or enveloped in thick atmospheres of hydrogen and helium. Their diversity suggests multiple formation pathways, from scaled-up terrestrial planets to stripped-down gas giants. Some may host deep global oceans beneath dense atmospheres, while others may be high-pressure rocky worlds with exotic mineral phases. Closely related are mini-Neptunes, which occupy a narrow size range yet show dramatic variation in density. Slight differences in mass can determine whether a planet retains a thick gaseous envelope or becomes a dense rocky body. This sharp transition, sometimes called the radius gap, provides crucial insight into atmospheric loss and stellar radiation over billions of years. Among the most extreme discoveries are lava planets. These rocky worlds orbit so close to their stars that surface temperatures melt rock into vast magma oceans. The surface may glow red-hot, while rock vapor forms thin, transient atmospheres. In some cases, material may evaporate into space, creating comet-like tails of dust and gas trailing behind the planet. Such planets represent the end state of intense stellar irradiation. Some exoplanets defy the very idea of a stable planetary system. Rogue planets wander through interstellar space without orbiting any star, likely ejected during early gravitational chaos. Though cold and dark, they may retain internal heat for long periods, raising the possibility that subsurface oceans could exist even in the absence of starlight. Orbital configurations themselves can be strange. Some planets orbit their stars at extreme angles, even moving in retrograde motion opposite to the star's rotation. Others follow highly elongated orbits, experiencing dramatic swings in temperature over a single year. Systems like Kepler-16b orbit two stars at once, producing double sunsets and complex illumination cycles that once belonged purely to science fiction. Composition adds another layer of strangeness. Carbon-rich planets may form with chemistry dominated by carbides rather than silicates, potentially featuring diamond-rich interiors. Water worlds may contain hundreds of kilometers of global ocean, with high-pressure ice layers separating the ocean from the rocky core, limiting geological interaction. These strange worlds are not rare exceptions. They are common outcomes of planetary formation. Their existence forces scientists to revise models, incorporating migration, atmospheric escape, stellar radiation, and chaotic interactions. Each exotic planet broadens the definition of what a planet can be. Exoplanets and strange worlds demonstrate that the solar system is only one expression among countless possibilities. By studying planets unlike anything familiar, scientists gain a deeper understanding of the physical laws that govern all planetary systems. These discoveries remind humanity that nature is far more inventive than imagination, and that Earth's particular balance is neither typical nor guaranteed, but the result of a long chain of fortunate circumstances in a universe full of extremes. Planets matter because they are the natural laboratories where the laws of physics, chemistry, and time express themselves in the most complex ways. They are not passive objects orbiting stars, but evolving systems that record the history of matter from cosmic dust to structured worlds. By studying planets, humanity learns not only how worlds form and change, but how order emerges from chaos on scales vast enough to shape destinies. At the most fundamental level, planets test physical laws under extreme conditions. Gravity, thermodynamics, fluid dynamics, and electromagnetism operate simultaneously within planetary interiors, atmospheres, and magnetospheres. No laboratory on Earth can reproduce the pressures inside a gas giant, the temperatures on a lava world, or the radiation environments near a massive planet. Planets therefore serve as natural experiments, revealing how matter behaves when pushed far beyond human-engineered limits. Planets also preserve deep time. While stars tell the story of nuclear fusion and cosmic energy, planets record the quieter but equally important processes of cooling, differentiation, and surface transformation. Craters, rock layers, and atmospheric compositions act as archives spanning billions of years. Through planets, scientists reconstruct the early history of the solar system and place Earth's formation within a much broader cosmic timeline. Understanding planets is inseparable from understanding life. Life does not exist in isolation. It is shaped by gravity, atmosphere, temperature, chemistry, and stability. Earth demonstrates how delicate this balance can be. Its long-lived magnetic field, active geology, moderate gravity, and stable orbit created conditions where life could not only emerge, but persist and diversify. By comparing Earth with other planets, scientists identify which factors are essential and which are incidental. Planets also teach humility. Early assumptions that the solar system represented a typical planetary arrangement were overturned by exoplanet discoveries. Strange worlds, hot Jupiters, super-Earths, lava planets, and rogue planets revealed that Earth-like conditions are not the default outcome of planet formation. This realization reframes Earth not as a standard example, but as a specific and fortunate result among countless alternatives. Beyond science, planets shape humanity's future choices. Exploration reveals resources, hazards, and limitations that inform decisions about expansion beyond Earth. At the same time, studying planetary failure, worlds that lost atmospheres, overheated, or froze, offers cautionary lessons about environmental stability. Planets show what happens when balances break, providing context for understanding climate change and long-term sustainability on Earth. Planets also influence perspective. Seeing Earth as one planet among many alters how humanity views borders, conflicts, and priorities. From a planetary viewpoint, distinctions between nations fade, replaced by shared dependence on a single, fragile world. Planetary science, therefore, has cultural and philosophical impact, reshaping how humanity understands itself within the universe. The search for life elsewhere sharpens these questions further. Each potentially habitable planet forces reflection on whether life is rare or common, fragile or resilient. Even the absence of detected life carries meaning, suggesting that complex life may require an unusually narrow set of conditions. Either outcome, abundance or rarity, deepens appreciation for Earth's significance. Planets also connect scales of existence. The same processes that form planets around distant stars shape the materials in human bodies. Calcium in bones, iron in blood, and oxygen in lungs were processed through stellar and planetary evolution long before life began. Studying planets is therefore a way of studying human origins at a fundamental level. In the end, planets matter because they tell the universe's story in slow motion. They show how matter organizes, how environments emerge, how stability can be sustained or lost, and how life might arise within physical constraints. Through planets, humanity gains knowledge not only of other worlds, but of its own, its past, its fragility, and its future possibilities.